so far, everything we've said about vectors is was taken from the perspective of algebra and arithmetic. So we defined a vector as a vertical list of numbers, and we said a few things about manipulating those numbers. Namely, we talked about scaling them by numbers, scaling them by scalars, and adding them together. But now I'd like to take a more geometric approach to the subject. So here's the punchline. Let's say we're talking about vectors in R2. Geometrically, we think of any vector in R2 as an arrow in the xy plane. So here we're looking at the xy plane, the Cartesian coordinate system that we all know and love. And I've just drawn an arrow floating around in the xy plane. So this is an example of a vector in R2. Now the question is, how is this compatible with our perspective on vectors, which says that a vector in R2 really should be a list of two coordinates? Well, the way that we extract coordinates from an arrow in 2 dimensions is by measuring tail to tip displacement. So what does this mean? Well, if we look at our vector that's sitting here in the xy plane, the arrow starts at a certain point. This is the point with coordinates 3, 1. This is what we call the tail of the vector. This is where the vector emanates from. So I'm calling this point the point P. And our arrow terminates at another point. This is the point with coordinates 8, 2, which I'm calling Q. This is called the tip of the vector. So if you just place an arrow in the xy plane, you can look for the tail, which is a point, and you can look for the tip, which is a point. And we have notation to refer to this. This is called displacement notation, maybe. So here we just write PQ with an arrow on top. And how do we get coordinates here? We look for displacement. So the idea is that we take the coordinates in the tip, and then we subtract the coordinates in the tail. So the first coordinate of our vector here will be 8 minus 3. Those are the x coordinates of the tip and the tail. So 8 minus 3 is 5. And then the second coordinate will be 2 minus 1. So again, the y coordinate of the tip minus the y coordinate of the tail. And that gives us the number 1. So here we've drawn a vector in R2. And it just so happens that this vector is the vector 5, 1. So this is the connection between the geometry that we're seeing here and the arithmetic or algebra that we developed before. Now, one interesting thing that emerges from this perspective is the fact that if we think about how we're thinking about vectors here, we're using vectors to represent displacement. We're not using vectors to measure location. So here I have the xy plane, and I've plotted what looks like 4 different vectors: a vector v, a vector w, a vector x, and a vector y. But if we think about the coordinates of these vectors, well, we can look and see what the x displacement and what the y displacement is for each of these vectors. And what we realize is for each vector, to measure the x displacement, we're walking 2 units to the right. So we're walking 2 units to the right for v, we're walking 2 units to the right for w, for x, and for y. So the x coordinate, or the first coordinate of each of these vectors, is 2. And then to get up to the tip of the arrow for each of these, we only need to go up 1 unit. So the second coordinate of each of these vectors is equal to 1. So even though these are 4 vectors in different locations in R2, they all have the same coordinates, so these are actually all the same vector. And the first time I saw this, it kind of blew my mind a little bit because I was used to thinking of coordinates as measuring locations in 2 dimensions in the xy plane. But this displacement perspective allows us to talk about problems from any location in R2. So if you were using one of these vectors to describe displacement in a certain direction, well, you could do that regardless of whether or not you're standing at the tail 1, 1, the tail 2, 0, the tail 5, 1, or the tail 6, 0. So if you were at any of those locations and were concerned with the displacement 2, 1, you could use this same vector. And one thing about arrows in 2 dimensions is they have a length. So let's say that the coordinates of our vector are v1, v2. We have special notation to refer to the length of a vector, and this is the double bar notation. In some books, I think if any of you are reading Strang, you'll find just regular absolute value notation. I kind of like this double bar notation because it reminds us that the object that we're working with is a vector, not just a number. But at any rate, the formula for length is equal to the square root of the sum of the squares of the coordinates. So for this vector v1, v2, the length is defined as the square root of v1 squared plus v2 squared. Let's see that in our example here. So we're back to our arrow that whose tail is 3, 1 and whose tip is 8, 2. We found that the coordinates were 5 and 1. So what that meant was that the x displacement for this vector is the first coordinate, which is equal to 5. And the y coordinate for this vector, which is the y displacement, is v2 equals 1. According to our formula, the length of this vector should be the square root of 5 squared plus 1 squared, which is equal to the square root of 6. And if we look at this figure for a second, we can't help, or at least I can't help, but think of one important theorem that might describe this situation, and that's the Pythagorean theorem. So the idea of the length of an arrow or the length of a vector in 2 dimensions is inspired by the Pythagorean theorem. That's where we're getting our terminology from here and our definition from. What about 3 dimensions? So let's say that we want to work with a vector v in R3 and we want to think about it geometrically. Well, in 3 dimensions, we don't just have the xy plane, but we have the xyz axes. Just as a little refresher, or as a new concept for those of you who have maybe never seen these 3 axes before, the idea of measuring location in 3 space is the exact same idea as measuring location in the xy plane, except now we have a third axis to deal with. So over here, so now let's say we're looking at these 2 different points. Let's focus on maybe this first point with coordinates 1, -3, -1. Well, what are these coordinates referring to as a location in 3 space? The idea is that to get to this location, we should walk 1 unit in the positive x direction, so that's maybe like this. Then we should go 3 units in the negative y direction, so we should go 1, 2, 3 units in the negative y direction, and then we should go 1 unit down, so in the negative z direction, so down here. So if we were measuring the location 1, -3, -1, this is how we would do it in the xyz space. Same goes for this other point over here. This is the location -2, 3, 1. To get to this point in space, we should go 2 units in the negative x direction. Then we should go 3 units in the positive y direction, and then we go up 1 unit, or 1 unit in the positive z direction. So here we just have 2 locations sitting inside of 3 space. And again, finding the coordinates of a particular location in 3 space is really similar to finding the location of a point in 2 space, except now we just have another coordinate to think about, which is represented by the z-axis. So a vector in R3 is viewed as an arrow in xyz space, and each arrow has a tip and a tail. So if we wanted to, we could use the points that we're working with here to construct a vector that emanates from 1, -3, -1, and that terminates at -2, 3, 1. Again, we use the same notation. P is the tail here, and Q is the tip. So it's appropriate to write V equals PQ with an arrow on top. And again, to find coordinates, we use tail to tip displacement. So this is exactly how the situation works in 2 dimensions, except we have a third coordinate to account for. So when we go to find our coordinates here, we'll take the coordinates in the tip and subtract off the coordinates in the tail. So the first coordinate will be -2 - 1, which is -3. The second coordinate will be 3 - -3, which is 6. And the third coordinate will be 1 - -1, which is 2. So the arrow that we're looking at right now has coordinates -3, 6, 2. And just like in 2 dimensions, we have a formula for length in 3 dimensions. It's the same formula as the formula for length in 2 dimensions, except again, we have a third coordinate to account for. So the length of a vector v, whose coordinates are v1, v2, v3, is referred to with the same notation. So we use this double bar notation. And the number we're referring to is the square root of the sum of the squares of all the coordinates. So this is the square root of v1 squared plus v2 squared plus v3 squared. So let's say that we were looking at our vector in 3 space. This is the same one from the previous slide where the coordinates were -3, 6, 2. If we wanted to find the length of that vector, we would take the square root of -3 squared, which is 9, plus 6 squared, which is 36, plus 2 squared, which is 4. And if I added everything correctly here, that should be the square root of 49. And I happen to remember that the square root of 49 is equal to 7. So we can simplify that here. So this vector that connects P to Q has length equal to 7. And again, the point here is that the length of a vector measures the distance from the tail to the tip. So now we get to the cool stuff. So if we understand how geometry works in the dimensions we can see, that is in 2 and 3 dimensions, well, what we can do is we can see that geometry and then figure out how formulas might work. And then we simply extend those formulas so that they work in higher dimensions. So how should we think of a vector in Rn if n is like a really big number, like 4 or 5 or even 100 or 1,000? Well, we simply view our vector as an arrow in space, just like we do in small dimensions. So if I'm just talking about a generic vector, regardless of whatever dimension it lives in, I'll simply represent it geometrically as an arrow. And the idea now is that the visible geometry of the smaller dimensions defines geometry in high dimensions. So, for example, we have a length formula that makes sense. How should we define the length of a vector with n coordinates? Well, we could extend the formula that we've been using. We've been using the formula that says that the length is the square root of the sum of the squares of all of the coordinates. That worked in 2 and 3 dimensions, so let's just always use that formula in higher dimensions. So by definition, we're saying that the length of a vector with n coordinates is the square root of the sum of the squares of all of the coordinates. So here, what I'm doing is I'm geometrically representing this particular vector, and this vector has 5 coordinates. So this is a vector in R5. I don't know what R5 looks like, but whatever it looks like, this vector is an arrow in that space, and length is defined as the square root of the sum of the squares of all of my coordinates. So here the coordinates are 4, 0, -2, -5, -1. So to calculate length, I'll square 4, I'll square 0, I'll square -2, -5, and -1. I'll add those squares together and take a square root, and I end up with the square root of 46. So whatever this vector is in 5 dimensions, its length is equal to the root of 46.